Welcome to this explainer. Today, we're diving straight into the mechanical heart of modern AI to figure out exactly how it works. I'm absolutely thrilled to guide you through this because we're going to decode the specific mechanisms that triggered the greatest technological leap of our generation. Okay, let's just jump right in.
So let's start with the ultimate question, right? How in the world did we go from those clunky, frustrating chatbots we all remember from just a few years ago to systems today that can write complex software code, generate stunning video from a quick text prompt, and literally pass the bar exam? I mean, it feels like magic, but it's really not magic. It all boils down to two vital pillars: architecture and scale. And to really grasp this, we have to look back at the massive roadblock that was holding us back for decades.
Section 1. The sequential bottleneck.
To understand the breakthrough, we actually have to look at the old way AI used to process language, which was known as recurrent neural networks, or RNNs. For a long time, this was the absolute gold standard. But old AI read text sequentially. I want you to picture a really slow reader dragging their finger across a page, pointing at one single word at a time, left to right. Because of this token-by-token processing, RNNs suffered from a major flaw that engineers call the vanishing gradient problem. In plain English, by the time the AI reached the end of a long paragraph, it had literally forgotten how the first sentence started. The information from those earlier words just became too diluted.
The fundamental bottleneck here was that sequential processing. And, it wasn't just bad for memory, it was completely terrible for modern computer hardware. We were stuck in the slow lane. Hardware like GPUs are specifically designed for parallel processing, right? They want to calculate thousands of operations simultaneously, but RNNs force them to just sit around and wait, doing one thing at a time. The parallel processing revolution was waiting just over the horizon, and it was about to change absolutely everything.
Section 2. The transformer breakthrough. The dam finally broke in 2017. Researchers at Google published a legendary paper with a slightly cheeky title, "Attention is All You Need." This paper introduced a totally new deep learning architecture called the transformer, entirely abandoning those old sequential methods. To picture how revolutionary this is, imagine replacing that single, slow reader tracing words with their finger with a massive team of thousands of readers analyzing a single document simultaneously. They're all reading at the exact same time, drawing these invisible string connections between related words, no matter where those words sit on the page. So the word bank at the top of the page is instantly connected to the word river at the bottom. No more forgetting, no more sequence bottleneck.
Section 3. The mechanism of magic. Now, how do they actually pull off that parallel reading? Well, this is the true magic trick of the transformer, a mechanism called self-attention. Think of it as a highly advanced information retrieval system. For every single word in a sequence, the self-attention mechanism calculates its exact relevance and mathematical relationship to every other word at the exact same time. It weighs the importance of the context. It figures out if the word apple means the fruit or the tech company by instantly looking at the surrounding words in parallel.
But here's a really crucial detail. The AI isn't reading letters like you and I do. Instead, it uses what we call word embeddings. It converts words into continuous mathematical vectors. Just imagine a massive, high-dimensional spatial library. In this library, concepts are assigned specific coordinates. So the concept of king and the concept of queen sit very close to each other. Dog and puppy are neighbors. The AI navigates this conceptual coordinate space to literally calculate meaning based on spatial distance.
So why does this matter to you? What is the real-world takeaway here? Because this parallel processing ability, driven by self-attention and word embeddings, is exactly why your AI chatbot can instantly synthesize an answer in milliseconds instead of taking hours. It's analyzing your entire prompt all at once, calculating the conceptual math, and generating the optimal response instantly.
Section 4. The scaling hypothesis.
Okay, so once the transformer proved we could process data entirely in parallel, an explosive new idea was born, championed heavily by researchers like Ilya Sutskever at OpenAI. The thinking here was remarkably simple, yet profoundly ambitious. If a tiny workshop can build a perfect toy using this transformer architecture, what happens if we build a factory the size of a continent using that exact same blueprint? If we just make it bigger, will it actually get proportionally smarter? The crucial point here is that OpenAI relentlessly pursued this hypothesis. They didn't get bogged down in endlessly tweaking complex architectures. They focused on scaling a relatively simple one. They threw unprecedented amounts of three core ingredients at the transformer: massive model sizes, internet-scale training data, and hundreds of millions of dollars in compute budget using thousands of specialized GPUs. To truly visualize this massive jump, look at what happened when OpenAI went from their GPT-2 model to GPT-3 in 2020. They expanded the model size 100-fold. They reached a staggering 175 billion parameters. And parameters are essentially the synaptic connections in the model's artificial brain. That kind of scale was just completely unthinkable before. But the absolute most fascinating part wasn't just the sheer size. At this massive scale of 175 billion parameters, the models spontaneously developed what researchers call emergent capabilities. These were skills the AI taught itself that it was never explicitly programmed to do. We're talking about chain of thought reasoning, translating flawlessly between languages, and even writing highly functional computer code. The model just figured it out purely because of the vast patterns it learned at scale. And guys, the momentum isn't slowing down at all. As OpenAI's CEO Sam Altman points out, scaling this architecture isn't just some fascinating science experiment, it's actually driving a fundamental collapse in economic costs. The cost of running these models is dropping by about a factor of 10 every single year. This plummeting cost structure is paving the way for what Altman calls radical abundance, which is basically an era where intelligence becomes as cheap and accessible as electricity. So I want to leave you with this final, provocative thought to chew on. We've seen that moving from millions to billions of parameters gave us systems that can code, reason, and pass complex exams. If just scaling up this one beautiful architectural mechanism, the transformer, got us here, what unimaginable capabilities are going to emerge when we scale it by another trillion parameters? Thank you so much for joining me on this explainer. Keep learning, and I will see you in the next one.